Hello students, today's video is the first video in Unit 3 using large and small numbers, logs, and orders of magnitude. Today's video is on scientific notation. Our learning target for this video is that by the end of this video you should be able to use scientific notation to represent large and small numbers and use standard logs. When we talk about scientific notation is just a way to write really large or really small numbers in a condensed fashion. So this is an example of scientific notation. We could use 5.67 times 10 to the 5th power, and that is the same as 567,000. So watch this quick video on a brief explanation.
Hey there everyone, and welcome back to Mashup Math. My name is Anthony, and thank you for joining me on this mini lesson. Let's just go ahead and check it out. Hello again. Thank you for joining me on this lesson where we are going to explore scientific notation. So let's start with the question, what is scientific notation? So let's start with a definition and then work from there. Scientific notation is a way of expressing numbers that are either too big or too small to be conveniently written in decimal form. Let's take a look at a really big number. The population of the state of Arizona is 7,200,000 people. And now we can ask, how can I use scientific notation to express this value? Now, if you remember from our definition, we're talking about numbers that can't be expressed conveniently in decimal form. And thinking about this number as a decimal, we can just add a 0.0 to the end as a placeholder for now. We do this because scientific notation requires that we figure out the number of place values in between the decimal and the first non-zero digit, in this case, 7. So now we can go ahead and count how many place values there are in between. And we can see in this example, there are 6 place values. So that number 6, that total number of place values, is an important number, and we're going to keep that close by to use in a few moments. Now we can imagine moving that original decimal point to the left until it is in front of that first non-zero digit, again, in this case, the 7. Now, when we're using scientific notation, we can now get rid of all of the zeros that come after the last non-zero digit. So in this case, all of the zeros that come after the value of 2. So now we have a much cleaner, much smaller, and much more manageable 7.2. But what about all of those zeros? Scientific notation allows us to replace those zeros with multiplying by the value of 10 raised to a power. In this example, the power is 6, which represented the total number of place values we moved the original decimal point. And we should note that whenever we are using scientific notation, we are multiplying by the value of 10 raised to a power. There will never be a different value other than 10 in that spot. So now let's take on another example of an even bigger number, in this case 29,700,000,000. So this is nearly 30 billion. This is a very, very large number. And we want to use scientific notation to rewrite this value in a more convenient way. So again, we can add 0.0 to the end of the value as a placeholder so that we can visualize where that decimal point would be. And now we have to figure out how many place values are in between the decimal and the first non-zero digit, in this case, the 2. So in this example, we can see that there are 10 place values in between the decimal and the first non-zero digit. And now we can remove all of the zeros that come after the last non-zero digit, in this case, the 7. So now we have 2.97 times 10 raised to a power of 10, which again was the number of place values that we had to move the original decimal. So really all that we did here was use scientific notation to rewrite 29,700,000,000 in a smaller and more convenient way. So take some time to think about the procedures and the concepts involved with scientific notation as you continue your exploration of using it to rewrite very large and very small numbers in an easier way. And I'll see you all next time.
Okay, so as you can tell from that video, hopefully this is something that you have seen before in your science classes, and so we're going to continue on with this going forward. So let's go over the rules for scientific notation. The first thing that you have to do is when you write that coefficient, the coefficient has to be between 1 and 10. And so in the video he talks about putting the decimal right after the first non-zero number, and so that's what you're going to do. Then the base of the times with the exponent, the base has to be 10. The exponent shows the number of decimal places that must be moved to change the number to standard notation. A negative exponent means you have a very small number. So when you're converting from scientific notation to standard notation, you're going to move the decimal to the left. So an example of this would be something like this. If I have 2.3 times 10 to the negative 5, well, since I have that negative exponent, that means I'm going to move my decimal to the left 5 places. So 1, 2, 3, 4, 5. This would be where my new decimal is, and then you have to lead it with a bunch of zeros. So put zeros in all those place values. So 2.3 times 10 to the negative 5 would be the number 0.000023. Now, if you have a positive exponent, that means you have a very big number, and so you're going to move the decimal to the right when you're converting from scientific to standard. So let's say I have 2.3 times 10 to the positive 5. Well, in that case, I'm going to move my decimal to the right. So we have 2.3, and I'm going to move it 1, 2, 3, 4, 5. Go ahead and put zeros in all of those places, and so it would be 230,000. So you take a second, and I want you to go ahead and try and write all of these numbers in scientific notation. Remember, scientific notation is going to be times 10 to some exponent. So take a second, pause your video, try these out on your own, and then when you're ready to check your answers, go ahead and press play. All right, check your answers, make sure that you've got them correct. One thing that I will point out is notice that when you have large numbers, so these right here are considered large numbers. And when you have large numbers, your exponent is always going to be positive. And then when you have small numbers, so these are all, less than 1, when you have small numbers, your exponent is the negative. I added this little website in here because it is really cool to play around with. It has the scale of the universe in scientific notation, and so you can click on different pieces of the universe, like the different planets, and it's just kind of a neat little thing to play around with. So try it on your own when you have time. Okay, now we're going to move into what we call the magnitude or logarithmic scale. So hopefully you remember how to convert from exponential to logarithms and vice versa from Algebra 2, but we're going to review that. Sometimes we need to scale very large or very small scales in the same place. Instead of linear, we may use a magnitude, power, or logarithmic scale. So if you look at this first scale, you can see that it has the powers of 10. So 10 to the first power, 10 to the second power, 10 to the third power. And so this would be like population. So the population of your family, the population of your class, the population of your school, the population of the city, state, and United States. Those all fall within those powers. Now, what we can also do is use a logarithmic or exponential scale that is based on the powers of 10. And so basically what we do is we just include the exponent. So 1 would be the log of base 10. 2 would be the log of 10 to the second power. 3 would be log to the 10 to the third power, and so on. And so you're going to see it both ways as we're moving forward. First, we need to review how to write in exponential form from a log, and then also vice versa, going from exponential form to a log. And so I want you to remember this from Algebra 2. If I have to write this log right here, and how we say this is we say that this is log base 2 of 8 equals 3. Okay, and so when you're saying that, that's how you say it. Log base 2 of 8 equals 3. Well, if you remember from Algebra 2, when we convert this to exponential, we're always going to start with our base. Our base is 2, and so we're going to now write that as an exponent with a base 2. The exponent is always what the log is equal to. So 2 to the third power, and then you wrap around and you say it's equal to 8. So you can always do this, but if you'll say it like this, log base 2, that's kind of reminding you that, oh, that is my base 2. So when I write my exponent, I need to use that base. Then whatever the log is equal to, that's your exponent. And then it's equal to this part right here. Okay, so hopefully you remember this from Algebra 2, but we will practice this over and over. So some common logs that we use. Anytime you have a log that has a base 10, that's just considered the common log, and so a lot of the times you'll see it just written like this, log of x equals y. Okay, this means the same thing as this. So if you do not see a base there, it's understood that that base is a base 10. Okay? Now, if we convert that to exponential form, remember, we start with our base 10, we pick this up as our exponent, and it's equal to x. So 10 to the y power is equal to x. All right, so if we convert y equals log base 2 of x, that would be equivalent to start with your base always, come over here, pick up your exponent, so 2 to the y power, and then it's equal to x. So without using a calculator, go ahead and compute these logs. Now I'm going to help you with these because I know it's been a while since you've seen these in Algebra 2. But when you have log base 10 of 100, basically what you're asking yourself is this. 10, because we don't know what our exponent is. We don't know what our exponent is. That's what we're trying to find. So 10 to what power equals 100? Well, hopefully you realize that that power would be 2. Do the same thing here. And I'll just go ahead and use x now. 10 to what power equals 10,000? And so what you're going to realize is that powers of 10 equal the number of zeros you have. So here I have 4 zeros, so that's 4. Now, when we do this, what does this equal? Well, notice that this is a small number. So 10 to what power equals 1 over 100? When it is a small number, remember your exponent is negative. So we know it's going to be a negative, and then now we just have to count how many zeros we have. So negative 2. Okay, let's go over to this one. So this one again is a very small number, and so we need to figure out what exponent is going to give us that small number. So 10 to what power equals 0.0001. What we can do is we can count how far we have to move the decimal to get to the end here. So 1, 2, 3, 4. So x is going to be equal to a -4. If you don't like working on it that way, you can convert that decimal to a fraction. So this would be 1 over, look at the place value, tenths, hundredths, thousandths, 10,000, so 10,000. And again, if you just look at the number of zeros that you have, and just make sure you put a negative if it's a fraction. All right, now let's look at these. Notice your x is in a different place. So if I convert this to an exponent, we start with our base, we go around to our exponent, and then we set it equal to this. So it would be 10 to the 4th power equals x. And so now just go ahead and solve that out. Well, 10 to the 4th power is 1 with 4 zeros. 1, 2, 3, 4. And so it would be 10,000. Okay? Going and looking at this one here, if I convert it to exponent, 10 to the -4 equals x. And so this is going to be a very small number because we have a negative exponent, and it's going to have, so we're going to start with it's going to have 0.123 and then 1. Okay, in this next example, they're wanting you to use a calculator. And so anytime you have a log base 10, if you go to your calculator, you're going to just use this button right here. This is the common log button, so if you type in log, and then you can just type in that number 5. Okay, so our first answer is 0.6989, and I would go ahead and have you round it to, I'd say, the nearest thousandths, but because that 8 is in the thousandths plate and we go 9 after it, that means we're going to round it up, so it would just be 0.699. Okay, going to the next example, if you do the log of 50, and I'm just doing that on my calculator, you can do it on yours, and if I round it to the nearest thousandth again, we have 1.69. It's 8, 9, 8. We look at the 9 after it, that means we round it up, so 1.699. Then if I do the log of 500, that comes out to be 2.699. And then if I do the log of 5,000, I have 3.699. Alright, so this video serves as a review over some scientific notation and then also just some log and exponent rules that you learned in Algebra 2. This is going to be the assignment that you're going to do in class when you come to class, and so if you want to go ahead and do this on paper, you can, but you are going to enter your answers on the Moodle assignment. Make sure you've taken good notes, and I will see you in class.